All right, so this is the last subunit, or sorry, last lesson of the stoichiometry unit. We're just going to identify the excess reactant and find out like how much is left over. So today, after today, we should be able to calculate limiting reactant. Um, we've already done this, but we have to do this to find the excess reactant, and we need to be able to calculate how much of the excess reactant will react, and how much will be left over. We're just going to do our first example. I think there's only one. No, there's two examples. We're going to do a limiting reactant calculation just to kind of refresh our memory. And then we only have one other example and we're done with the lesson, because you'll notice that everything is the same except on the last step, we're just adding two steps. We're going to identify the excess reactant, which is not the limiting reactant. And then we're going to find out how much is left over, which is a simple subtraction. So don't be, nervous. Let's do the limiting reactant calculation. So we have how many moles of iron oxide can be produced from the reaction of 13.7 moles of iron with 18.19 moles of oxygen. So the word equation, so how many moles of iron oxide can be produced? So that's our product, okay? So that's going to be on the right side. And the reaction will be iron with oxygen. So basically the word equation is iron with oxygen will have a synthesis reaction to form iron oxide. The formula equation, so iron is not a diatomic element, so it'll be Fe plus oxygen is a diatomic element, so it'll be O2. That will yield iron oxide. So this is an ionic compound. I know that because this is a metal. This is a nonmetal. It tells me the charge on iron right here. So it'll be iron Fe3 plus and then O with a minus 2. So you would bring the 3 down and the 2 down, and you will have Fe2O3. Okay, so that's the formula equation. As far as balancing, we have 1 iron here, 2 irons here, so we need to balance it. Okay, and those are the balancing. We have 4 irons here, 2 irons here. We have 6 oxygens here and 6 here, so we're good. So we're going to find the limiting reactant. So we have iron. We have 13.17 moles of iron, and we have 18.19 moles of oxygen. So we need to find out how much of this iron oxide we will make given those two amounts. So we're going to have two equations, one with the iron being the known and the iron oxide being the unknown, and one with oxygen being the known and iron oxide being the unknown. Okay, so in these calculations, the unknown will always be the same as far as finding the limiting reactant. So we always start with our known. The known will be, the first known is 13.17 moles of iron. Unknown, we're trying to find out how much iron oxide that'll create. So we have our known here, and then we need to cancel out our moles. Okay, so we already have moles, so we don't need to convert from grams to moles. We have moles already. So we have moles of iron here, and we got this number 4 from the coefficient. And with the iron oxide, we got the 2 from the coefficient as well. We're looking for moles of iron oxide. We are at moles of iron oxide, so we are done with this equation. Okay, so you just type it into the calculator, 13.17 times 2 divided by 4, and there's your answer. We're not completely done. We do have to find out how much 18.19 moles of oxygen will make, how much iron oxide that this much of oxygen will make. So our known, again, will be what the question gives us, 18.19, okay? And then our unknown is what it's asking, how many moles of iron oxide. So we always start with what we know, which is 18.19 moles of oxygen. We need to cancel out moles of oxygen, okay, so we can get moles of iron oxide. So we will use the coefficients that we find in the equation. So there's 3 moles of oxygen, which we put here. There's 2 moles of iron oxide, which we put here, okay? Then you just plug it into the calculator, 18.19 times 2 divided by 3, and we have our answer. To determine the limiting reactant, whichever number is smaller, okay, so 6 is smaller than 12, that's the limiting reactant. So the limiting reactant is, don't get confused by saying iron oxide is a limiting reactant, because that's what we're trying to find, how much. the limiting reactant is actually all the way over here in your known. So iron is the limiting reactant. Okay, so this is the new stuff today, the limiting reactant and excess reactant. So there's two parts to this question. The first part is what mass of cobalt chloride is formed from the reaction of this many atoms of cobalt with this many liters of chlorine gas at STP. And for those of you who are not honors, in honors we learned what standard temperature and pressure is. There's a certain temperature and a certain pressure that we have as a set standard, and I know that's obviously, but we in non-honors sections, we are not going to change temperature and pressure, which does, if you remember honor students, it does change the pressure or how much gas can fit in there if you change the pressure. So at standards STP, just know that that's at normal conditions. That means nothing special, just keep going. And in honors or IB, you will be possibly changing that temperature or pressure. Okay, so we want to know how much of it can be formed. Okay, so first we got to find the limiting reactant and then find out how much we can form. So whatever one's the lowest will be how much is formed. And then here's the new part, how much of the excess reactant reacts and how much is left over. So let's do the part we already know. So cobalt chloride is formed, so that's our product, and the reaction is cobalt, okay, with chlorine gas. And you would just balance the reaction, which I've already done here. So we're doing this part of the question first. So our known is what's in the question, okay? There's going to be two knowns and one unknown. The first known will be what's in the question, and then the second known will be here, and both unknowns will be what mass of cobalt chloride. Okay, so what mass of cobalt chloride? We always start with our known, what's given, okay, and then whatever's up here must go here, so that's where Avogadro's number comes in, and we need to convert to moles, okay. Since we don't have moles, we must always convert to moles first. So we will take this and divide by the atoms, and so now we have moles of cobalt. We need moles so that we can do our mole to mole conversion. Okay, so that's where you take your coefficients. So we have cobalt on the bottom and our unknown needs to go on top. So that would be cobalt chloride. Okay, so our moles of cobalt cancel. And we've got these twos. Okay, both of these twos came from their coefficients. So now we need to, our answer can't be in moles of cobalt chloride because it's actually asking for grams of cobalt chloride, which we saw here in the question. So we need to find out how many grams of cobalt chloride are in 1 mole so that we can find the conversion. So here we've done this. We just grab these numbers off the periodic table. Don't forget that you have 3 chlorines in the molecule. That tends to be a common mistake. And you have 165.13 grams of cobalt chloride per mole. Okay. So you just write that. That's a conversion. This is not, so this will always be 1 mole and this will always be 1 mole. The only time this won't be 1 mole is when you're doing your mole to mole ratio. Now you just plug it all into the calculator. So you could cancel out these times 10 to the 23rds if you were comfortable with that. So in your calculator you would do 3.478 divided by 6.02 times 2 divided by 2 times 165.13. And you do whatever you're comfortable with. Some kids will, or some students would know that this would actually be 1, so they would stop that, and some are very comfortable with taking off the exponent, whatever you're comfortable with, or you can just do the whole thing. So we have our answer after we've plugged it in. Now we have to do the second set, okay? We know how many grams of cobalt chloride that this many atoms of cobalt will produce. Now we need to know how many grams of cobalt chloride that 57.92 liters of chlorine will produce. Okay, so the unknowns are the same. And your known will go here, okay, always. Now we need to convert. If it's not moles, we need to convert to moles, okay? So to convert to moles, that's the 22.4 we're familiar with. And then now that we're in moles, okay, we've canceled out our liters of chlorine. Now that we're in moles, we need to do our mole to mole ratio, and this is where we get our coefficients from the chemical reaction over here. and then the moles of chlorine will cancel, and we at least have the correct element or a compound that we're dealing with. However, it's not asking for moles of cobalt chloride, right? It's asking for mass, grams, okay? So we need to convert that to grams, and we don't have to re-add how much cobalt chloride weighs because we've done it over here. All right, so we have our correct units, and now when we plug all of that into the calculator, we have this number. So the limiting reactant is whichever one is lower. So 95.4 is smaller than 284.7. So that means this is the limiting, this is how much you can make, okay, given those two numbers. This is the most we can make, and the limiting reactant is cobalt, okay? So that means the limiting reactant is cobalt, okay? If the limiting reactant is this one, that means the excess reactant, the reactant that's left over, will be chloride, okay? So the chlorine gas will be left over, and the cobalt will be the limiting reactant. So once cobalt is gone, the reaction will not occur anymore, and we will have excess or extra chlorine gas. Now, we're going to do something else. So it says how much can be produced. So this is how much can be produced, okay? So some of the questions on your homework and your test will ask you which one's the limiting reactant. That means you have to tell me what the limiting reactant is. That's cobalt. If I were to say how much can be produced, that means this is the maximum that can be produced. So make sure you're reading your question right. You don't want to get a question wrong because you just answered it thinking it was one thing and you didn't read the question very well. So this is the excess reactant, and it's just going to ask how much is, so the next slide we're going to talk about how much of the excess reactant reacts and how much is left over. So in order to do that, there's another problem we have to do, okay? So we're going to have to do using the limiting reactant as the known and the excess reactant as the unknown. Okay, so the known will be the limiting reactant, which is cobalt, okay, and it gave us this in the problem, and then the excess reactant is the unknown. So how much of the excess reactant, is left over. So then our unknown will be liters of chlorine. That's our excess reactant, okay? And now you just kind of follow the rules of dimensional analysis. You have your atoms of cobalt here, and then you have your atoms of cobalt here, okay? This is just a conversion. Now you need to do your mole to mole ratio, okay? So we have our mole to mole ratio here, and it's just like any other mole problem, except we're just going one step further and using only limiting and excess reactants. So all of this is the same as the last slide as far as steps involved. If you don't have moles, you need to convert to moles. If you have moles, then convert to whatever unit the question's asking for. So in this case, how much of the excess reactant reacts and how much is left over. So this is the excess reactant. We need to find out how much chlorine is left over. So you need to know that chlorine is a gas. It tells you in the question, but in order for you to find out what unit to use, okay, here and in the unknown, you need to know it's a gas. So just kind of use your clues, I guess. So then you calculate that, okay? So the times 10 to the 23, they'll cancel out. So in the calculator, just type in this number divided by 6.02 times 3 times, divided by 2 and times this, okay? And there's our answer. That is how much will react, okay? So that's how much will react, not how much is left over. In order to find out how much is left over, you have to take what you calculated first and subtract this, and that's how you find out what's left over, okay? So now we're almost done. So to find out how much is left over, you take how much reacted, which was our first slide, okay? That's how much we calculated would react with this much, if we had this much, okay? And then cobalt wasn't limiting. So then we take the amount that we just calculated and subtract them. Okay, so that's how much is left over. So there's a difference between how much is in excess and how much is left over. So we'll do a practice problem so that we can see it together, and then we'll also do it in class as well. All right, let's do a practice problem from the homework packet. I chose the last one because I figured by that time... Sorry, by that time you're a little tired and you want a little help. Plus, number 4 is pretty well explained on the homework answers on Moodle. So let's do this one together. What volume of butane can be produced at STP? And remember that just means standard temperature and pressure. From the reaction of 13.45 grams of carbon with this much hydrogen gas at STP. Which reactant is in excess? So we're doing a limiting reactant, plus we're doing excess reactant problem, okay? So we don't have to create our word formula or anything. It's done for us. It's balanced. So let's just get right into it. We need 2 knowns, okay? So we have a known and an unknown. And then we will have another known and another unknown, okay? The knowns will be what's given in the problem. So 13.45 grams of carbon and 17.65 liters of hydrogen gas. And then our unknown will always be the same. What volume of butane can be produced? What volume of butane? Sorry, the kids across the hall are a little noisy, but it's passing period, and you guys just finished your midterm. That's when I'm recording this video. So there's actually, you guys aren't in school, and I am doing videos after I graded your tests, and so they kind of have the school to themselves, the kids across the hall from me. So they're not really being rude. Okay. So we're going to find out which one's the limiting reactant and excess reactant first. So that's our first step. Right. So we're going to start with our known, which is 13.45 grams of carbon times something. Okay, so we have grams. We need to convert to moles so we can do our mole to mole ratio. And then, since we don't want to be answering in moles, we're going to have to convert out of moles to liters, okay? So we need to convert grams to moles, so grams of carbon to moles of carbon. Then we're going to do a mole to mole ratio, okay? Whatever's up here must be here. And then the other thing we're trying to convert is moles of C4H10, okay? So we are given a known, convert to moles, mole to mole ratio, convert out of moles and into the unit we need. So the unit we need is liters of butane. And we will have to be getting out of moles of butane. Let me give myself some more space for because I know it's a conversion, so it'll be 1. Okay, so we just need to plug in some numbers, and that's going to not be so bad. So this is conversion as well, so it's just going to be 1 mole. Grams of carbon, I just grabbed that number from the periodic table, which is right here. So 12.011. And then we do a mole to mole ratio. So this actually is a 1 here. It's just kind of assumed. So 1 mole here, 4 moles here. Okay. And then we have our number, and then this is just a conversion, and we know what that number is. It's 22.4. Hopefully you do by now anyways. All right, so now we just plug it into the calculator, and we will have our answer. All right, so 13.45 divided by 12.011. We don't really do times 1, we just ignore it. So divided by 4 times 22.4 equals. You don't have to do parentheses or anything when exponents aren't involved on this problem. It does the order of operations correctly. Your calculator usually does it well, and you just do it. So we have 1, 2, 3, 4 significant figures. So 1, 2, 3, 4 significant figures. The 6 will round the other 6 to 7. So 904.7. 904.7 liters of butane, C4H10. Okay, that's 1. We need to do the other so that we can compare and find out which one's lower. So our known is 17.65 liters of hydrogen. Okay, and the steps we can just kind of go ahead and do this. So all we're doing is filling things in. So we have liters, so we must convert to moles first. Okay, and we need to get out of liters. Okay, we need to convert from liters to moles so we can do our mole to mole ratio. Okay, so moles of hydrogen will go here, and then moles of butane will go here. Okay, and then we need to convert out of moles and back to liters of butane. Okay, so moles of butane, this will be a conversion, so we can write 1, C4H10, sorry. And that is 22.4 liters of butane. Okay, so we have most of the stuff filled out. I know that for every 1 mole, there's 22.4 liters. 22.4 liters of any gas at STP. And then mole-to-mole ratio, so for every 5 moles of hydrogen, we will have 1 mole of butane, and everything else is filled out. Okay, so 17.65 divided by 22.4 divided by 5 times 22.4. And that's, we have 4 significant figures. We only have 3 in our answer, so we're just going to kind of leave it at that. 3.53. I'm not about to try to make up numbers. 3 liters of butane. Wonder if I did something wrong, because that's a huge difference. Okay, nope. I don't notice anything that I did wrong. So the limiting reactant is this one. This is the lowest number by far. So this is the limiting reactant. So the limiting reactant is actually, liters of hydrogen. So hydrogen is limiting reactant. Excess reactant will be carbon. Okay, so in order to find out the excess reactant, how much is left over, we need to find out first how much will react. And to find out how much will react, we will do another mole calculation with a known and an unknown. Okay, except the known this time will be the limiting reactant. I almost forget every time. Limiting, which is H2. So we have 17.65 liters of H2. And then the unknown is going to be the excess reactant, because that's what it's asking for. So unknown will be how many, what is it, carbon? So it's not going to be liters, because carbon's not a gas. Carbon is going to be mass, okay? So because it gave us, oops, you can't see. It gave us mass up here. Carbon's not a gas, it is a solid, so it'll be how many grams of carbon. So we don't have moles at all, so we're gonna have to convert to moles, do a mole-to-mole ratio, and then convert out of it. So our known is 17.65 liters of H2. We're gonna have to convert to moles, mole-to-mole ratio, convert out of moles. Okay, so first let's convert to moles of H2. That means 22.4 liters of H2, mole-to-mole ratio. Okay, so this will be moles of H2 because that's what's up here. Where we need to go is carbon, so moles of carbon. Then we'll have to cancel out moles of carbon. It'll be a conversion. And then we'll have to go to grams of carbon, okay? All right, so let's fill in some numbers. For every, let's look up here. So moles of carbon, for every 4 moles of carbon, there are 5 moles of hydrogen. And then grams of carbon, we're going to grab that off the periodic table, 12.011. All right, now we just plug it in the calculator. So we have 17.65 0.65 divided by 22.4 times 4 divided by 5 times, oops, I pushed divide, delete, times 12.011. And our answer will be, we have 4 significant figures, so 1, 2, 3, 4, so 7571. Grams of carbon. This is how much will react. Wow, I can't spell. Rect. Get wrecked. React. There we go. So that's how many grams of carbon will react if we had, this is how many grams of carbon will react if we had this much hydrogen. Okay, so there's going to be leftover carbon. Now what we need to do is we need to subtract what the problem gives us with carbon. Oh, you can't see that. What the problem gives us with carbon minus how much reacts, and then we have our answer. So the problem gives us 13.45 grams. That's what the problem gives us, minus 7.571 grams of carbon. Okay. $5.879. What's it called? Significant figures, this would actually be 5.88. Actually, let's keep that and just say 5.88 grams of carbon. That's how much would be left over.